Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Today is the last lecture of this NPTEL subject on this applied computational fluid dynamics. So, we have learnt a great deal about the different schemes that we use in CFD, the stability of those schemes, accuracy of those schemes, and we did little bit about finite difference, we learned about finite volume, and we also looked at some of the codes implementing those schemes. Then we spent a great amount of time in understanding Reynolds average Navier-Stokes equations, RANS, and then 1 week on LES also. In between we also discussed about the boundary conditions, and we talked about different kind of boundary conditions that we use. In this final lecture, I am going to show you some of the cases that will help you basically setting up the simulation if you want to employ a problem or you want to solve a problem, right. So, I will be using OpenFOAM for showing you these cases, although we have also shared some of the MATLAB codes. We have seen those in the class, how to solve the shock tube problem, okay, using the MATLAB code, and you can actually write an extended version of that MATLAB code for 2D and you can solve simple problems. If you want to go to 3D or solve basically more complicated problems, I would recommend that if you want to write a code, use either C, C++ or Fortran kind of languages, because then you can parallelize, you can use MPI and run the codes in parallel. Okay, for large size problems, MATLAB is not recommended. Let us say your problem size becomes, your grid size of your flow becomes more than a million or so, then you might want to parallelize it, so that you can get good efficiency and solution in a reasonable time. Okay, so I will be discussing about how to solve some problems using OpenFOAM, because that is an open source solver and you can easily use it the way you want. Okay, but the same philosophy is applicable to any solver that you want to use. Okay, maybe it is Fluent or Star CCM Plus or COMSOL. There are many solvers in the market where you can use the same philosophy of setting up initial condition, boundary condition, thinking about the flow, how to set up a computational domain, how to set up a mesh, and so on and so forth, right. So, I am showing you examples of OpenFOAM because it is an open source solver. You do not need any license there, or you do not need to pay for the commercial license. Okay, so you can try and gain some knowledge, and then you can use your own favorite solver, or you can write your own code if you are interested, right. So, first I will discuss some of the incompressible flow code flow problems, and then we will go to the compressible flow problems. Okay. So, the one problem that we have been discussing for a very long time is the lid driven cavity, right. So, here as you can see that the three sides are the wall and top is the moving wall, right. So, the top wall is moving at a certain speed, right. So, the question is how does the flow develop if you change different flow conditions, right. So, the boundary conditions are very easy for this problem. Three side is stationary walls and the top is the moving wall, right. So, the flow condition what will be typically known to you is, for example, what is the dynamical parameter which is governing the flow, right. So, in this case it is an incompressible flow. Okay. So, the only parameter that is governing the flow is the Reynolds number, right. I have taken a Reynolds number 400. So, if you look at the literature, this problem has been analyzed for a large number of parameters like different Reynolds number, different Mach number, different aspect ratios, different boundary conditions, where you basically you can move one lead or two lead or three lead, different shapes like triangular cavity or maybe other shapes also, right. So, we will take a very simple problem. Top lead is moving, 3 are stationary, and Reynolds number is 400. Because incompressible flow, there is no discussion about the Mach number here, right. So, Mach number is very small. right. So, another thing you should know about incompressible flow is that the absolute pressure does not matter, what matters is the pressure differential, right. So, unlike in compressible flow where you have the relation of P equal to rho R T and absolute pressure has got a meaning, we have discussed in the classes that in the case of incompressible flows it is a mechanical pressure and there is no relation between pressure, density and temperature. Okay. Although the systems are coupled, but what really matters is the pressure gradient, right, and not an absolute pressure. Okay. So, if you know the Reynolds number here in this lead dependent cavity flow, okay, so you need to solve this problem and you need to finalize what are the dimensions that you want, right. So, there are three things that governs the Reynolds number. So, U, L and nu. You can also let rho U L by mu, but because it is an incompressible flow you can take rho as a constant, right. So, then it becomes U L by nu where nu is the kinematic viscosity, right. So, you can choose two among these quantities U, L and nu and you can determine the 3 from the Reynolds number because you have to respect the Reynolds number that is given. That is the only parameter that is going to dictate how the flow is going to be, right. So, L is 1. So, here the Reynolds number is based on the lead velocity and the size of any side, right, the length of any side. So, you can choose length to be 1, okay, that is not necessary, you can choose length to be 0.1, 0.01, whatever thing you want, but whatever value that you choose you have to basically confirm that Reynolds number is coming to be 400, right. So, for example, we can take L equal to 1 meter, okay, U you can take 1 meter per second or you can take 10 meter per second, 100 meter per second, whatever thing you want, right. Accordingly you get the value of kinematic viscosity based on the Reynolds number, right. So, because nu is U L by R E. So, if you have U as 1, L as 1, then it becomes 1 by 400, that is 0.0025 meter square per second, right. If it is let us say if you take U equal to 10, then it will become 0.025, right. So, you can take any value you want, but you have to make sure the Reynolds number is 400, right. And then what are the steps that you need to do? First you need to, domain is already given, it is a well defined problem, okay. Each side now you have finalized that my length is going to be 1, right. So, you can take 0 to 1 in x and 0 to 1 in y, create a mesh, okay, choose an appropriate solver, right. So, it is an incompressible flow. So, you have to look for what are the solvers in the incompressible flow, okay. So, you have many solvers if you go to open form, there are solvers for the incompressible flow, the solvers for the compressible flow, right. So, usually solvers which are with for the compressible flow they have rho in front of them, okay, usually, but not necessary, there are solvers like sonic form also which is for the compressible flow. So, but like rho simple form or rho pimple form or rho central form, okay, these are the solvers which are for the compressible flows, right. When it rho is in front it means that the rho is varying there. If you go to fluent for example, you have like pressure based solver and density based solver, although it is not necessarily basically segregation between the incompressible or compressible, right, because the pressure based solver can also be used for the compressible flow problems. There you can call the energy equation and solve the compressible flow problems, right. So, coming back to how we are going to solve this on open form. So, we are going to decide how many number of grid points you want x and y, how many you want in y, choose a solver and flow type means whether the flow is laminar or turbulent, right. Reynolds number is very low here 400. So, we will choose the flow type to be laminar. So, no need to call in the turbulence model. Provide the initial condition, boundary condition, time step and so on and so forth. You can visualize the flow, you can compare with the data and then you can do the study with the at the different Reynolds number and find the effect of Reynolds number if you want, right. So, these are the things that we know L equal to 1, U equal to 1 meter per second and nu equal to 0.0025 and as I told that the pressure does not matter. So, you can take that P to be 1, P to be 0, right, or any value it will not matter. The one thing you must note in the case of open form, in the incompressible flows you do not give the value P, but rather you give the value of P by rho, okay. In the compressible flow you will give the unit of you will have P which is the thermodynamic pressure, unit is Pascal, right, or here you will have the quantity which is P by rho, okay. So, let us solve it on an open form solver using an open form solver, okay. So, Let me just go here. Okay. I hope it is visible to all of you. I have already opened this tab. So, I am using my cluster here to solve the problem. Okay. Okay. So, OpenFOAM is installed here. Okay. And there are multiple versions of OpenFOAM. In fact, OpenFOAM is maintained by at least two different repositories, but there are more versions also, right. So, one comes like version 10, version 11, version 12 and so on and so forth. Other is like 22.06, 22.12 and so on and so forth. Okay. So, you can check what version is installed. Okay. So, right now I am using OpenFOAM version 23.03. Okay. So, now I have made already some cases in NPTEL tutorials, okay, and then I am going to use this cases, and let us say I am going to solve this incompressible flow problem, the cavity problem using IICOFOAM. Okay. So, IICOFOAM, as the name suggests, it is an incompressible flow solver. Okay. So, there are many solvers present in OpenFOAM. Those who have not used OpenFOAM till now, please go back and take a look. You have already many solvers and many tutorials given there. In fact, you can edit those solvers to solve your own problem, right. You just need to find out what is the appropriate solver that you need. There are solvers which are made for the transient problems, like where the flow is varying with time, unsteady problems. Okay, and there are solvers which are made for the stationary problems, which is steady state problems, right. So, IICOFOAM is a very simple solver. I think is the most basic solver. Okay. And it uses, so if you want to know what kind of scheme it is using, you can go to this system and FV solution. Okay. So, it uses a scheme called piezo. Okay, this is an algorithm in incompressible flow. The two algorithms which are very popular, one is simple and another is piezo, right. It is using piezo algorithms. Basically you split the equations. So, this is implicit splitting operator. I will not go into the detail. My purpose today here is to solve some problems, okay, but you can always go and find the details of what kind of solvers that you are using. Okay, now look at the mesh. Okay, so for simple meshes you can use this block mesh, but you can also create mesh in any mesh generator and export it to OpenFOAM. Okay. So, you can see here, so these are two vertices, and by default the OpenFOAM is a 3-dimensional solver. Okay. So, even if the problem is 2-dimensional, which is what we are solving here, the square lead driven cavity, you have to give something on the third dimension, which can be very small, but you have to provide it, and this in fact you can do in your solver also. If you have some other solver which you have developed, it is a 3D solver, and if you want to solve a 2D problem, you can give some faces on the third dimension and put an empty boundary condition or maybe a symmetric boundary condition, and that would give you the solution in the third dimension. So, here you can see if it is 2D, you could have just like 0 0 1 0 1 1 and 0 1, that will give you 4 vertices, right. But because the 3-dimensional setup, which is what is honored by OpenFOAM, so we will be using the coordinates in 3 dimension, and you can see that in third dimension we have used only the variation of, I mean the width in the third dimension is just 0.1, right. So, all the flow is happening in 2D only. The third dimension is only because your equations are 3-dimensional that you are solving, right. And here I am using 100 grid points in both x and y, okay, and 1 grid point in the z direction. Okay. And I have given the boundaries here. This is top in the moving wall, okay, and then we have other fixed wall, and this front and back is basically this is coming up because you have solver is 3D. So, you have to have the empty boundary condition on the z direction, right. So, you can think of, let us say if this is your cavity, lead driven cavity, so you have certain width in the third dimension, right. So, that width I have taken to be very small, and I have put the empty boundary condition on both these sides, this side and this side, right. So, now we have made the changes in the block mesh dict, okay, according to the way you want, okay, and we have used the side width as 1 and number of grid points are 100. Okay. Now, what you want to do is you do block mesh. Okay, just call this block mesh and it will basically create the grid. Okay. You can see it has given what is the number of cells, you have 100 cross 100, so you have 10,000 cell points. Okay, and this is the box, okay, which is you can see in 2D 0011, and then in the 3D it's the width is 0.1, right, and these are the boundaries you have. Okay. Now, you have to go to finalize what kind of flow that you want to simulate. Okay. So, you can go to these transport properties, okay, and all you need to provide here is nu, okay, the kinematic viscosity. If it is a turbulent flow, then you have to give the other properties also, like what is the turbulence model that you want to use, but right now only the viscosity is enough because we are solving a laminar flow. Okay. Now, you go back and then you have to provide the initial condition and the boundary condition, right. So, the way it works in open form is if you open, let us say I am opening this field u is the velocity, okay, it is a vector, it will have like all three components u, v and w, right. So, the first thing it tells is what is the dimension. So, this is meter per second, right, this is m, l, t, and there are the units here, and this is the internal field which is a kind of equivalent to initialization. So, you have to initialize your simulation from something, right. So, what I am saying that everywhere the velocity is 0 inside everywhere, and at the boundaries we have some boundary conditions. So, this boundary field will not change, but internal field will evolve due to the equations and the boundary conditions, right. So, you have top is the moving wall. So, I am saying that keep the value of the velocity fixed, u as 1, v as 0 and w as 0, right. All three are other three are fixed walls, you said no slip boundary condition, that means as we discussed that your u velocity, v velocity and w velocity all are 0, okay, no slip and no penetration, and front and back is empty, that is coming because the solver is 3 dimensional. Okay. You do not need this if you have a 2 dimensional solver, right. Now, you have to do the same for the pressure also. So, the two variables here in the incompressible flow, pressure and velocity. So, you can take the velocity of the pressure to be anything. So, we are taking as 0. So, as we discussed that what matters is the pressure gradient and not the absolute pressure in the case of incompressible flow. You can see the unit here, okay, this is meter square per second square, right. So, that is because this is p by rho, this is not p, but p by rho. So, this mistake many people do, that in open form they try to give the value of pressure, rather you need to give the value of pressure by density here. Okay. Similarly, as we saw in the transport properties, you do not give the value mu, you give the value of nu, which is mu by rho, right. And as we discussed that for on the wall you can get the pressure by using a Nyman condition. So, just the 0 gradient on both the walls, moving wall as well as fixed wall, and front and back as empty, right. So, now we have set up the initial condition, boundary condition, we look at the flow type. Now, you go to system, okay, and then you can see the control dict. Okay. What kind of solver you are using? icoform. Okay. You can do it start time or latest time. Okay. So, we can set it if you want to restart the simulation or from 0 time. Okay. And what is the maximum time that you want to go? Okay. So, whatever folder. So, as we run this simulation, we will see that it will create different folders, right, and we are solving saving this at different time steps. Okay. So, for example, write interval 500. So, every 500 it will save. Okay. So, purge write is 1 or 0, that means you want to overwrite on the folder or you want to basically create separate folders. So, if you make it 0, okay, so it will basically keep on creating those folders. So, if your flow is unsteady or transient, you should make it 0, so that you can look at those data. And then these are like you want binary format, or what is the precision that you want, time format and all these things. Okay. So, these are not very important, you will learn about it as you try solving more and more complicated problem. There is also this decompose part dict, which I will not go into detail, but you can basically divide the computational domain into different parts. Okay. So, here for example, we can make 3 parts in the x and 3 parts in the y, and total subdomains will be 9, right. So, we have already created the mesh, right, using the block mesh. You can also do check mesh. Okay, so it has checked the mesh and everything is fine here. Now all you need to do is call this icoform. Okay, and you call this icoform. Now it is the simulation is running. Okay, so I have said that okay, run it till time equal to 10. So it will run the simulation, and I have already run and saved it here on the local. So this is running on the cluster. Typically if you have a large problem, you try to use cluster because there only you can fit the large problems. On your local desktop, trying to solve, if you try to solve a very large problem which has got millions of grid points, several millions of grid points, it may not be able to fit in because you do not have enough memory to fit in that kind of problems. Okay, so you can see that it is giving you some information about the Courant number, what kind of solver that you are using. Okay, and every time it is also reporting the residual. Okay, so it is going to get finished now. Okay, so we have already gone to around 9. So this is how you will run the simulation. Okay, you can also basically plot it like you do in Fluent. You can also see, you can write a small Python code maybe and see how things are changing with time. Okay, so I have actually given it for 20 iteration. Okay, so I have already solved it, downloaded it and saved in my computer. So what you can do, you can use ParaView and open the solution, right. So you can directly open using ParaView, or you can create a simple I mean there will be a paraform file. So you can directly use paraform, just go on the port, I mean terminal, and just type paraform, it will open the solver. But because we are running on a cluster, so there is no visualization there. So I have to download those files on the local system and then do it. So that is what I have done here. Okay. So this is the case of LDC. Okay, and you can see that I have created a simple file a.form. Okay, you can give any name. So what it does is basically it is a kind of patch in OpenFOAM. So that will help you open or visualize the data files in ParaView. Okay, so you can just do okay, apply. Okay, so you can see that I am seeing something. This is the pressure field. If you go to, let us say, velocity. Okay, this is the velocity magnitude. This is, for example, the x velocity. This is y velocity, and this is time equal to 10. If you go to 20, this is how it looks like, right. So different times you can see how your x velocity and y velocity is changing. So this is expected. See the top, you can see the color is red here, whose value is 1. So you have given the velocity boundary condition as 1. So that is honored here, and then because of that velocity, the flow inside that starts moving, and that is how you can see that that structure forms. You have all stationary walls here, but the flow is moving, and that is why you see this kind of shape. And if you go to the y velocity, so there was no velocity in the beginning, v was 0 everywhere in the initial condition, as we saw in the internal field, but now that has evolved here. Okay, you can also plot verticity and many other things that you can analyze. What I am going to do, so I have written a little solver in MATLAB which will visualize this and plot it and compare against the data which is there in the literature. Okay, so let me go there. Okay, downloads, OpenFOAM, LDC. Okay, so now I think LDC analysis. Okay, so what it does, it basically goes to the folders. Okay, so if you go to the constant folder, okay, it has got points everywhere. So you can see this boundary, face, neighbor, owner, and points, right. So we will go and look at the points. Okay, and we will find out the coordinates of that grid. Okay, so that is what I am getting, x and y, and then at a given time, which is I have taken the time as I believe 20. Okay, directly is 20. So I am going at t equal to 20 because the solver has run for 20. Okay, you can see here. okay, this is there for 20, and at every time you can see that it has created u. So, this is the we had started, if you look at the file at 0, you had given some velocity which was uniform 0 0 0 in the internal field, but with time it developed, and now you have this new velocity field, and every point is 10,000 points, it is giving velocity field everywhere, this u velocity, v velocity, and the w velocity, right. So, w will show 0 because we are not considering any variation in the third direction, right. So, we are opening the velocity and the pressure, okay, using this MATLAB code, okay. Let me make this, okay, if I can make this size bigger, okay, fine. So, I am reading those files of the velocity and the pressure, okay, and I am plotting those quantities what I saw in the para view, okay, plot settings. Okay. Yeah. So, now I am analyzing the flow. Why it is creating like this? Okay, because I moved the file. Okay. So, now you can see here the same thing I am plotting using MATLAB, but you can use Python or any other tool. So, typically I advise all the students that if you want to analyze a flow, get the data in a format that you understand. Okay. Of course, the TechPlot and ParaView or Nsight, these tools are there to help you visualize the flow, but if you want to quantitatively see how the flow is looking like, qualitatively you can easily see using ParaView. Even quantitatively you can see, but it will require some effort, but if you understand the data you can manipulate the way you want. And what I am doing here is that the blue points that you see is from the simulations by a paper authored by Ghia and Sin, 1982 paper in JCP. This is a very famous paper. I have given the reference to that paper in our slides. Okay, so you can see that I am able to plot this contours here, and then I think this is v by infinity. So, the v velocity, and I am plotting the variation of the v velocity at midpoint, okay, x by L equal to. So, so at the midpoint of y here, from here to here I am plotting, and you can see that it goes high and then comes down, that is red region when it goes high and blue region when it goes low, right. So, the left one what you see is a qualitative plot, that it makes sense. Okay. So, first thing whenever you do a simulation, you have to qualitatively see whether the things are making sense, when my top lead is moving, whether the flow that I am expecting because of the movement is coming or not. Once you have the qualitative validation, you go for the quantitative validation, that means how accurate my solution is, right. So, you can see that now I am plotting this solution here and it looks quite accurate, although you can see that there is some mismatch here. So, then the next step would be to the grid convergence. So, right now I am using 100 cross 100 grid, you might want to use 200 cross 200 and see how things are varying, right. So, we just did a simulation of the lead driven cavity flow incompressible using icofoam. Okay. Now, we go to the second problem and we will go to the compressible flow. Okay. So, we will try to solve the same problem using lead driven cavity problem using a compressible solver, right. So, same problem, but right now we do not have only the Reynolds number, but also the Mach number, right, because it is a compressible flow problem. So, I have chosen a smaller Mach number 0.2 because I will be using the data from the incompressible solution and compare the results, right. So, as you increase this Mach number, it will deviate from the incompressible flow data. So, that is expected. Now, when you have compressible flow, you have the variation of rho, and you will have variation in T, right, and P equal to rho RT relation will come in, right. So, in this case only Reynolds number and Mach number will not be sufficient to determine the flow conditions like pressure and velocity. You have to basically define or basically take one of these three values, the density, pressure or temperature, that needs to be known. Okay. Typically I use temperature because in a given flow temperature does not vary too much in the free stream. Let us say you are doing experiment in a wind tunnel, okay, unless you are doing experiment at a very low temperature or very high temperature, typically you can take the room temperature, so maybe 298 or 288, right. So, from that, so if you know the temperature, you can get the value of the speed of sound, you can calculate the value of u, and you know the u, L is fixed by the dimension of the body, okay, in this case cavity, okay. Mu also can be determined using T, using the Sutherland's law, right. We have seen how the Sutherland's law can be used to calculate the viscosity, and from that you get the value of density, and from density you can get the value of pressure P equal to rho R T, you know the temperature and the density. Remember, you cannot give arbitrary value of the pressure in the compressible flow solver because that is a thermodynamical quantity, and that has to be correct, accurate, right. So, in this case, for example, I have taken temperature equal to 288, assuming air is the medium, right. So, molecular mass is around 29 gram per mole, gamma is 1.4. So, these things are fixed, and you know the value of the gas constant, right. So, that universal gas constant, you know, 8314.5, and you know the molecular mass, you calculate the specific gas constant, which is R, calculate the viscosity using the Sutherland's law, calculate the speed of sound using square root of gamma R T, calculate the velocity, which is Mach number multiplied by this speed of sound, get the rho from the Re, because R equal to rho u alpha mu. So, you know everything except rho, get rho from Re and get P from perfect gas equation P equal to rho R T, right. So, you see that using the only three information, temperature, Mach number, Reynolds number, we found every single quantity. Okay. So, we have to honor, so many times students get confused that in the incompressible flow we got the velocity, or you can calculate the velocity from the Reynolds number, right. So, when it is compressible, typically you get the velocity from the Mach number and use that velocity in the Reynolds number to get other quantity, like for example density. But this is not the only approach, okay. You can have density instead of temperature, okay, or you can have maybe pressure may be known instead of temperature, right. So, you can manipulate these equations to get all the variables, but what you need to make sure that both Reynolds number and Mach number are cannot change, okay. That is the flow condition, that is the governing parameter, right. So, we will use the same approach, okay. Create mesh, you have to choose a solver which does this in a compressible manner, initial condition, boundary condition, and then what you can do at your home is that you can change the Mach number and see how the what is the effect of the Mach number. So, let us look at how we are going to solve it. Okay. So, first I am going to show you this example soft tube, yeah. Yeah, so this is a little MATLAB code. So, I am giving you the mu reference as this is for the Sutherland's law, gamma is 1.4, universal gas constant is 8314.5, molecular mass is 28.9, okay. From the molecular mass and universal gas constant, you got the specific gas constant, which is R equal to RST by mm, okay. And then these are the conditions given, okay. We calculated mu using the Sutherland's law, okay. So, this is the Sutherland's, okay. Now, you got the speed of sound, okay, and then we got the velocity, then density, and then the pressure. If you run it, okay. So, this is at Mach number 8.8, you can do for 0.2 also, if you just change the Mach number. So, you will get the new value. So, for example, the velocity is 68, rho is 1.05, P is 8.7147. So, you do not have to specify all three, okay. You have to specify only pressure and temperature, and density will be calculated, or you can specify only pressure and density and temperature will be calculated using the ideal gas equation. So, what solver we are going to choose now? We are going to choose a rho simple form, okay. That is also a steady state solver, and we know that flow is Mach number is very small and the Reynolds number is very small. So, it is going to be steady. So, let us go to this okay. Okay, this is Mach 0.8. I will change it to Mach 0.2 RSF. Okay, RSF is row simple forms. It uses a simple algorithm, but it also uses an energy equation. So that's why we call it row simple form. Okay, so now, so I will just clean this case. Okay, form clean tutorials. Okay, so now I think everything is gone here. So we had the solution up till 5000. Now it is gone. Now you have to go to the system first. Okay, and you can see this control dict. Okay, so I am using row simple form starting from latest time. I am running till 5000. So this you have to, you will learn from the experience that how it is going to work. Okay, how long you have to simulate. Okay, typically around 20 flow times or so is good for the flow to evolve, but it may require more also. Okay, and this is when we are writing, and all other things are simple. Okay, if you go to the constant directory, okay, here there are two things here, the thermophysical property and turbulence property. We did not have the thermophysical property in the case of incompressible flow, right. So what does this thermophysical property do? So you have to say that what kind of equations you are solving. Okay, so here we are using equation of sensible internal energy. So remember we had discussed the many different forms of the energy equation in the Navier-Stokes equation, right. So you can write in terms of total energy, internal energy, enthalpy. Okay, so all these forms are possible. So you are using sensible internal energy. Okay, equation of state is perfect gas. Okay, species you do not worry unless you are solving for multiple species, like in combustion you are using the Sutherland's law for getting the viscosity. If you make it constant, then viscosity will not change, and these are the values of the Sutherland's law, constant. Okay, and as constant, for example, tells that how your Cp and is going to vary. So here we are saying that Cp remains constant, which is given as 1005. This is a molecular mass. This will be used to calculate your specific gas constant. Okay, and these two will be used to calculate your viscosity. Okay, and we are not assuming any variation in the HF. Okay. Now you can go to the turbulence properties. Okay, so here you can use a turbulent simulation or the laminar simulation. So I am doing it laminar. Okay, so you can remove this part if it is not RAS. RAS basically Reynolds averaged. Okay, so because the Reynolds number is very low, we are doing for the laminar flow. Okay, so if it is turbulent flow, then you can call it remove this laminar and call it RAS, and then you can put the model that you want, like epsilon model, turbulence, and whatever quantity that you want, you can put in there. Okay, now let us go to the initial condition and the boundary condition. Okay, you can see now we have 3. Earlier we had only 2, but now we have 3, T, U, and P, right. So if you go to P, right, so it requires the value of pressure. So what is the value that you have got pressure? 8.7147, right. So you go there and change the value of this 8.71 value to 8.7147. Okay, and similarly you have to change the value of velocity also. Okay, what was the velocity here? So 68.1176, that for Mach 0.2. Okay, 68.1176. Okay, and now since we have assumed the temperature, so you can have to give temperature also. I am taking the temperature as 288, right. And for the temperature and pressure, we are using 0 gradient for the walls and front and back are empty. Only for the velocity, we are using a moving wall and no slip for the fixed walls, right. One thing you very important that I want you to note is the unit of pressure here. Okay, so if you recall earlier the unit was 0, 2, minus 2, that is meters per second square. Now here the unit is MLT, right. So this is kg per meter second square. okay, because now it is the actual pressure, the thermodynamic pressure, right. So, we have set up the initial condition, boundary condition, solver we checked up. I will be sharing these files with you, okay, so that it will help you. So, you just need to do row simple form, okay. I have not created the mesh. So, it says that there is no poly mesh, that means I have not created the mesh. So, first thing is to do the block mesh, okay. You created the mesh, now you run the solver, okay. Now, it is running the solver, it will take some time. So, in the interest of time, what I have done is I have downloaded the files here, okay, and kept here, okay. This is for up to 5,000, okay. Now, I will do the analysis of this, okay, and run this. The code is very similar to what we had for the incompressible. The only thing different here is that now we also get this rho and the T, okay, or you can get the pressure also, okay. So, how do the solution look like? Okay, so, you can see that earlier it was matching quite well on the top, but now it has gone down, that is effect of the Mach number. So, as flow becomes more and more compressible, okay, so it will deviate from the incompressible part, okay, and here also it goes little bit up. So, that is the effect of the Mach number. You can run with different Mach numbers 0.5, 0.8 and so on and so forth, and see how this curve is changing for the lead driven cavity. You can plot different parameters also. I am just plotting V, but you can plot U, vorticity, all these quantities you can plot and see how things are changing. Okay, so, now we solve the lead driven cavity using the incompressible flow as well as the compressible flow. Okay. In the compressible flow, it takes it is taking a little bit more time, because it is also solving for the energy equation, right. Now, we will go to the third problem, okay, which is the shock tube. So, this problem we have already seen and we have solved using our own solver, okay, written in MATLAB in 1D. Okay. So, here we are going to solve it in using open form. So, the conditions well known, I am not going to discuss it a lot. So, we have high pressure on the left, low pressure on the right. At T equal to 0, the diaphragm breaks, and you have expansion fan on the left, shock on the right. Okay, and these are the conditions that you need to put. Okay, so let us set up this simulation. So, because this has got shocks, so typically two solvers are better for shocks. One is sonic form, another is row central form, right. So, let me show you the setup for both. Okay, so it has already done, but we have already discussed that. Okay, so let us go to the shock tube. This is sonic form. Okay. So, whenever you use a solver, make sure that you read about how the solver works. Okay, what is the scheme that they are using, let us say in sonic form or row central form. So, row central form is very close to the central differencing scheme. Of course, you require little bit of dissipation, but the dissipation is very small. So, that is why it is more accurate, but the Courant number that you require is very small in the case of row central form, because as we know that central differencing scheme is typically not stable. If you add very little dissipation, then you have to make sure that Courant number is very low. So, typically the row central form works if your Courant number is let us say 0.2 or 0.3, okay, maybe 0.4, but not more than that, it will blow up. But like solvers like row simple form or sonic form, they are stable for higher Courant number also, right. So, here you can see that there is velocity 0 everywhere, it is a shock tube problem. Okay. Yeah, before that I should show you the geometry or how we have made the grid. Okay. Yeah, you can go to this block mesh dict. Okay. So, what I am doing here is basically 100 points in the x direction and 10 points in the y direction, right. It is effectively it is a 1D flow, right. So, I am solving it in 2D manner. So, 100 in the x and 10 in y, and we can see the flow at the center of the this domain, okay, and Z it is just 1 because it is anyway an empty boundary condition, right. And in the x variation it is minus 0.15252 to 0.1525, in the y it is minus 0.03 to 0.03, right. So, that is the variation that we have. Okay, and this is taken considering that we are going to compare the results at a particular time, right. As we have seen the shock tube, I mean as the shock moves, we want to consider it at a given time, and it should not go beyond the this domain. So, that is how we have considered it, right, and these are different sides. Okay, so, now go I start with U. Okay, so, we are anyway interested in the middle section. So, it does not matter or I mean on the top and bottom you can put a symmetry boundary condition, okay, and then you have zero gradient conditions in on one of the sides. Okay. So, on the left and right you can put a zero gradient, and top and bottom you can put the slip, okay, and then if you go to pressure. Okay. So, we have like given a distribution of ratio of 10. So, like 30,000 to 300,000, right. So, these are the pressure because we are solving it in a dimensional manner, okay, and then you go to temperature. So, the temperature also do not have to give anything, okay, and yeah, you go to the thermophysical properties. So, here you can see that transport I am keeping is constant. So, I am not using Sutherland's law. So, I am not asking the solver to vary the viscosity with temperature. So, you can just keep the viscosity is constant, and moreover it is an because we are comparing with the analytical solution. So, the viscosity is 0. So, it is an inviscid flow. So, I am putting mu equal to 0 and transport equal to constant, that is why, right. Here also I am using sensible internal energy, and air is I mean the mixture is air, okay, and Cp is around 1005, okay, but anyway H is constant here, okay. So, all other things done. Okay. You can go to the control dict, okay. I am using sonic form. I am simulating up to 0.00025, okay, and you can see the delta T is very small for it to run. And here also you can see that how do you basically change the time, right. So, adjust time steps, if you make it adjust time step equal to yes, it will basically change the delta T every time based on the Courant number which is allowed, right. So, I am saying maximum Courant number is equal to 20, maximum delta T is this. So, this will get applicable if you do adjust time step equal to yes, otherwise it will go with the delta T that you have given here, okay. So, let me run this block mesh, and then you have to do sonic form, okay. So, now it is solving, and I will show you later maybe, or maybe I just stop and show here that now you can see that it is solving for ux, uy, ug, energy and pressure, right. So, depends on what kind of solver you use, whether it is pressure based or density based. In the pressure based also you can have the energy equation, right. So, that way it can solve either for pressure or some other quantity, right. You need 5 equations, right. So, here it is solving 3 momentum and enthalpy, and finally it is solving for pressure, okay. So, let me show you the solution here first, okay. This you can go back and run and see the solution, yeah. So, this is the sonic form, okay. So, you can maybe perhaps open it on this also. So, the shock tube, because I have loaded, I had not unloaded the other one. So, let me just make it big, okay. You can see the shock tube, and you can see that it looks slightly 3D because open form, as I told you, it is a 3-dimensional solver, but you can probably make it yeah, just you can visualize it maybe said, yeah. So, the rate, I mean go to the velocity, that will make more sense, okay. So, you have higher velocity on the left hand side, Okay, so depending on how you plot, so you have basically shock moving on the right hand side and expansion fund moving on the left hand side, right. So in order to do it, in order to see it variation, let me do in MATLAB. Okay, shock tube examples, open form, analysis shock tube. So I am also going to compare with the analytical solution. Okay, and this is the time step 0.0025. At this time, I am going to compare the analytical solution as well as the open form solution. Yes. Okay. So what are the quantities that I am plotting here? Okay, so the first I am plotting is pressure, the top is pressure, and second is temperature. Okay, so the top is the pressure. You can see there is high pressure here on the low pressure here. Okay, and finally you can see the variation here. Okay, so the red one that you see is the analytical solution. We have already discussed this analytical solution earlier, and the blue one what you see is the solution using open form using the sonic form solver. Right, you can see that there is a lot of dissipation in these places. It is not able to basically capture the sharpness here, and that is a typical feature of any dissipative solver, that it gets dissipated near the discontinuity, right. So you can see it. You can increase the resolution and get this discontinuity better, I mean predict the discontinuity better, but what we will do, we will use the same thing for the row central form solver, which is a more accurate solver. Okay. So I will just show you here system. Okay, so I am now using the row central form, and we are going to the same time, okay, that we required, and here you can see that okay, here also I am not using the maximum Courant number that you allow, I mean that is allowed for this particular solver is around 0.3, 0.4. If you go more than that, then it will get blown up, okay, because it is a complex, it is a solver based on central differencing. Okay, I will just remove this folder. Okay, and then just let me run this row central form. Okay, so here this is a density based solver, unlike the sonic form, which is a pressure based solver. So there we saw that we are solving for ux, uy, uz, and then p and e, right. Here you can see there is a it is a solver that we have been discussing a lot in our course, right. You are solving for rho, which is the continuity equation, and rho ux, rho uy, rho uz. Okay, so it is solving in the conserved manner. Okay, and finally the rho e, right. So it is solving for all 5. So this is I think the only solver in open form which is density based. Of course, there are more solvers which are coming every day, right. So here you can see that you are solving for all these 5 equations in compressible manner, and let me plot this. Okay, so I have run it already, and I am just going to discuss with you how it looks. So go to RSCF. Okay, maybe this is the one. Yeah. So qualitatively it looks very similar to what we had for the sonic form, but if you look at quantitatively, you can see that it is captured much better here. Okay, the peaks are captured much better here because it is a more accurate solver than the sonic form. Of course, it is more expensive. The time step that is allowed here is very small compared to the sonic form, but captures much better. And if you see the comparison between the two, okay, yeah. So here is the comparison between the two. Okay, you can see here that SF is the sonic form and RCF is a row central form, and the row central form captures very close to the analytical solution for the same grid resolution compared to the sonic form. But as you may also realize that you can see there is a kink here, right. So, these are the features of the any solver which has got less dissipation, right. For example, the central differencing scheme, right. So, those kinks are present here also. These kinks get smooth end when you use a dissipative solver like the sonic foam, right. So, it is a always a comparison between what you want more, like whether you want more stability or whether you want more accuracy, and unfortunately they are not I mean you cannot go with both. Okay. So, we did the short shock tube also. Now, just I want to show you that you can use other way of non dimensionalization also. So, this is for example, supersonic flow over a forward facing step and shock gets formed. I will show you the structure very soon, and there is a tutorial given here. I would suggest you to go back and do the tutorial. So, here you can see that we are using a Mach 3. So, inlet we are using inlet boundary condition here, the Mach number is equal to 3 and the pressure is 1 liter per meter square. So, how do we get the value of parameters so that your Reynolds number and Mach number are honored. Okay. So, first let me take you to the solver. Okay. I think it is okay. So, this is the default solver that we have there, and if you go to the velocity, so it is taking the velocity is 3, the Mach number is 3 and velocity is also 3, right. That means your speed of sound has to be 1, right, and then your pressure is taken as 1, okay, and these are all quantities which are physical, okay, and temperature is also taken as 1, okay. So, your temperature is 1, pressure is 1, velocity is 3, and you have to make sure that Mach number is 3, okay. And if you go to the system here, thermophysical properties, you can see the molecular weight is very high. So, typically if you do it for air, you would expect the velocity should be, so the molecular weight should be 28.9 or 29, right, but the molecular weight is very high. Cp is also very different, earlier it was 1005, it is 2.5. So, how did it happen? The mu is 0 because we are doing for inviscid flow here. Okay. So, if you go to turbulence properties, it is anyway inviscid flow, so laminar and mu equal to 0, okay. And then I think we are solving it using system using row central form, okay. I will first show you the results which I have obtained using the solver. Okay, so, this is the forward step. Okay. Yeah. Okay. So, this is the shock structure that I was telling you. Okay, there is shock which goes up and then it gets reflected, okay, then it gets reflected again. This is a typical case of your shock structure which gets developed in the case of forward step. So, you can see there is a step here, the supersonic flow which is coming from the left, okay, and because of this step here you have a bow shock which gets developed, okay, and then the shock basically because it is an inviscid flow, you have a Mach stem here, this gets reflected here back and then it gets reflected again. So, this is the solution that you are going to get. Now, how did we set up this flow, okay, how is it set up in the open form, right. So, let me just open the MATLAB file and show it to you. Yeah, this is forward step, okay. So, your let me run it. Okay. So, I am not considering this molecular mass of 28.9. So, what I am rather doing is I am taking a pressure equal to 1, temperature equal to 1 and your speed of sound is equal to 1 and Mach is equal to 3, right. So, you have this Mach equal to 3. So, you can find out what is the value of R, right. So, you have give the temperature is given and the gamma is given, gamma cannot change. So, gamma is 1.4. So, this I think perhaps I should comment out. Okay. Okay, yeah. So, I am getting this R and you can see this R and D value 0.7143. So, my gas constant is coming out to be 0.7143, and why is that? Because of our choice of speed of sound and the temperature, right. So, if your speed of sound is 1 and temperature is 1 and gamma is 1.4, what is the value of R? So, that I calculated, which is 0.7143. Now, your universal gas constant is constant, right, 8314.5. So, then only thing that you can play around is the molecular mass. So, if you want to get the molecular mass, you have to divide this. So, your molecular mass, your specific gas constant is universal gas constant by the molecular mass, right. So, the molecular mass will be the universal gas constant, which is given as RST here, divided by the specific gas constant that you got, right. So, that will give you 11,640, right, and then you have to get the Cp also, right, based on that gas properties. So, that will be gamma R by gamma minus 1 and R we have got put its R and D is 0.743, the Cp also gets changed, and then you will get is Mach into A, Mach is 1. So, A will become Mach is 3 and A is 1. So, you will become 3, right. So, what we did here in this particular case, instead of changing the properties of U and V, what we did, we basically changed the gas property itself, right. We change the gas property where the molecular mass is now 11,640 and Cp is 2.5. Anyway, the mu value is 0. So, the Reynolds number does not matter, but we just use the Mach in number information of 3 and we got other values, right. So, you can play around with all the quantities that you have in your hand, but you have to ensure the dynamical parameters do not change, right. So, if you have Mach number here, Mach number should not change. If you have Reynolds number, then Reynolds number should not change. If you have both of them, then both of them should not change, right. So, this one example I want to tell you show you, so that you can understand this. Okay, and finally, there are several examples in open form. There are several tutorials that you can work out and you can experience for yourself how things work. Okay, and finally, this is an homework which I want you to do at your own pace. So, you can read this paper of high speed flow simulation using open form, and they have given several cases. One of the cases supersonic flow over a wedge. Okay, so, you can take this case, okay, make your grid, run the simulation, look at the shock structure, analyze the flow, and finally compare against the available result which is there in the literature, right. So, I want you to do it so that you get some confidence of how things work, and this will really help you, and with the understanding of the overall course that you have about the boundary conditions, about like how to create a domain and how to select a solver, I think you should be able to solve it. I have not shown you example of the turbulent flow, but there are several examples there where you have to select the turbulence model that you want if the flow is turbulent, and then different coefficients you can set up. The beauty about this open form is that you have the source code available. You can change the coefficient that you want the way you want. Okay, you can modify the code. You can add your own turbulence model or transitional model and see how things work. Right. So, this is the end of the course, and I hope you enjoyed it, and I hope that you will be able to make a career in CFD and solve some problems which are really interesting and which is in your domain. Okay, good luck, and hope to see you in another course. Thank you very much.